815 rats that gave birth to some number of babies. Okay, and if we divide these numbers, number of rats here, by 815, we get these relative frequencies. So intuitively, these relative frequencies may be considered as the probability that a rat gives this many number of uh, gives birth to this number of babies, right? So we can consider these two sets. The set of rats. So rats. Actually, there are 815 rats in this set. Okay. And on the other hand, we can consider a subset of real numbers, which is integer from 1 to 12. Okay. So some rat gave birth to one baby. Another rat gave birth to two babies. So there should be a mapping here. Okay. So this mapping is a random variable in this case. Okay, so this function can take values of 1 to up to 12 according to this table. Okay. In this case, in order to define a random variable, we need to define a measurable space, right? So we have sigma here. What's the sigma algebra in this case? Usually, if this sample space is countable, we usually take sigma algebra as its power set. Okay, so that means this is the set of all subsets of omega. Okay, so in this case, the sigma algebra is the power set. Okay. Then, remember the definition of the probability measure? It is a function from the sigma algebra to this interval, real numbers between 0 and 1. Okay, so this probability measure is defined for this sigma algebra. So what is this function in this case? Okay, actually we don't know. But since we don't know anything about this experiment, I mean we know something but not much about those rats. So we assume that each rat appears with equal probability. Okay, we just close our eyes and pick any rat here. So every rat has the equal probability of being picked. So in that case, we can define the probability of each rat. So each rat. So one rat is a subset consisting of one rat is equal to 1 over the size of omega, which in this case is 815. So we just take equal probability. Okay. So we just used the principle of indifference. Okay. If we don't have any information about the details, we just assume everything happens with equal probability. So that's called principle of indifference. Principle of indifference. Okay, you should study what this really means. Just look up Wikipedia. Okay, so we know we can assume probability is like this. Since each element here is disjoint from any other elements, so by defining the probability of each rat like this, this is not just element, it's a subset consisting of one element. Okay, so what subset is an event, and by defining this we can define the probability of any events. Okay, because for example, let's pick any subset here, let's call it A. So the probability of this event subset A can be calculated as the sum. Probably I should write first. This A is a union of all elements in A, a union of this type of subsets. So subset consisting of one element, and this element belongs to this A. Okay, so this A is equal to this union. But these subsets are obviously disjoint, so we can, according to the third axiom of probability measure, we can split this into the sum of each event. But we define this probability measure as this, which is a uniform distribution. So this probability is equal to 1 over 815. So this is a constant. There is no omega here. So we just count the number of elements in A. Then we get the probability of event A as this. Well, which is actually better to write like this. So we can calculate the probability for any events. Okay, now after defining this probability here, we can derive the probability distribution for the values of random variables. Okay, so what is the probability, for example, that the number of the liter size is 1, for example? How do you calculate this? So in order to calculate this, we look for the inverse image of this. This is 1 point, but we can make it a set consisting of this 1 point. Then we can calculate the inverse image of this set, of this subset. Okay, so certain number of rats here have produced one baby. So we can calculate the probability of this in terms of the event as a subset of omega. Okay. So, okay, let's say this random variable is called x. Okay, it is, by convention, we usually write random variables by a capital letter like this, x, y, also by capital letter. Okay, and another convention is we write the values here, values by lowercase letter like x, small x, large x. So, please distinguish these concepts. This is a random variable, which is a measurable function. And this lowercase x is a value like 1, 2, 3, and so on. Okay. So what we want to calculate here is the probability that the random variable takes the value of x, like 1, 2, 3, and so on. So we want to define, in order to calculate the probability, we want to define the event corresponding to that. Okay, what is the event corresponding to this event? Okay, so we have to define a subset of omega that corresponds to this equation. So that is, let's write it Lx, which is a subset of omega such that this random variable takes the value of this given value, x. Okay, for example, let's say x is 1, so L1 is a subset of omega where this random variable took the value of 1. If this is 7, it's a subset of omega such that this took the value of 7. Okay, so just pick 7 here, then we map this set of 1 value into this, then this is the event that corresponds to this value. Okay, so to use the notation we defined previously, we can write this as x inverse of x. So x inverse of 1. Oh, it should be capital letter 7. Okay. Then we can calculate the probability of this. Okay, so so according to our definition of the probability measure, this probability is just a ratio of the sizes of this set to the size of this set to the size of the sample space, which is the number of rats in this set divided by 815 in this particular case. Okay. So these values for each of x1 to up to 12 corresponds to the numbers we have seen in this table. After all, okay. So let's consider another case. What about the okay, and yeah, let's explain about this one. This is histogram. We just plot the number of the values of the random variables here, x-axis, and the relative frequency on the vertical axis. So it's just these numbers here. These numbers are plotted here like this. So this is very simple for discrete random variables. Okay. So far so good. Then we define the cumulative distribution function. Okay. Oh, okay. By the way, this this event is usually written as this. So we write like this: x equal to x. Okay. For simplicity. Okay, but what this really means is just this. Okay. Not x. It's omega. X of omega, it's lowercase x. You know, this argument of the probability